Welcome to another test and teardown video. This time it's a Polytechnic Research and Development Company Incorporated. That's impossible to say. Anyway, it's a type 587A UHF frequency meter. If you look at this from a distance, you'll think, oh, that's a camera. That's actually what I thought first time I saw it. Oh, weird connector for this camera. What kind of video picture is that? Wow, high definition stuff. Of course, this has absolutely nothing to do with what this really is. This is a cavity filter. In fact, a bandpass filter. So there's a resonance cavity in here, and the plunger that you move back and forward, you make it longer and shorter, and this way you create a resonance. And the two end connectors at each side, there will be a little antenna in here in the cavity. So the electrical signal goes into a radio wave signal that is in resonance with the plunger in here, and then it is coupled again to the output antenna and making the signal into an electrical signal. So this is how it works in a very brief explain. So the plunger is connected to like a dial, and it is geared with a very fine gearing here. So when you move this, you can actually see the distance here gets shorter and shorter, right? I get in and in and in. So the lowest frequency I can do is 250 megahertz, and see what happens here. I get out and out and out, and then I'm adjusting the center frequency of my filter. Let's see what is the highest frequency this filter can be adjusted to, and I think that is, we're close, aren't we? I'm getting tired in my fingers. Okay, so that was 1,000. So from 250 megahertz to 1,000 megahertz, that is the frequency range of this bandpass filter. So there's another thing. Obviously, we have a mechanical resonance room in here, and this filter is of course only designed to be used in this frequency range. So what happens if you apply a frequency range that is way higher than this frequency range? Obviously, you're going to expect some other things that's going to happen. We're talking about waveguide modes. And the waveguide modes kind of skip through the normal resonance systems. So you're going to see some other frequency where frequency is much higher than the adjusted frequencies, where it actually will be in resonance, and signals will go straight through the filter. So this is just a way that it works. You should just only use this for frequencies where the spectrum is within the accepted range of this product. I'm going to show you guys this because I took my spectrum analyzer here, and I'm now in 3.2 gigahertz from more or less 0 to 3.2. So that means the range of this unit is actually from here and down. So a quarter of the screen is the operating range of this filter, and like you can see here, I have a flat line. That is because I connected input and output together. So now I'm going to take these two end connectors and put them on my filter here, and let's just go for 1,000 as the first try. Oh, now we're connected to the spectrum analyzer, and I fine tweaked this a little bit, and see again, here is the marker at 1 gigahertz. where we got a pass. So that means all the other frequencies that's below 1 gigahertz, we got very, very deep attenuation. So that is amazing. Let's try and dial the marker to 1.5 gigahertz. See, 55 dB attenuation. So that is of course fantastic. But look at that one. And this is exactly what I said. This is the double frequency. So 2 gigahertz. There's of course also a resonance where you have a pass through. But look at that one. This is, what is that? That is 2.5. Isn't that a little bit funny? So those are the phenomenons that's happening in this unit. I bet this one is 3 gigahertz. Yeah, no, it's 3.1. So that is what's going to happen. And let's try and do something funny. And now I'm going to slowly dial this down to 500 while we look at the screen here. Oh, hang on, I will put a holder on my camera. So now we've got a holder on the camera, so I can dial. So this is from 1 gigahertz. Now I'm dialing down in the frequency. So that was 800. I bet this one is at 800. Let's try and dial the. So that's 2.5. So this is funny. Still 2.5. Okay, 19. And that one is probably, oh, see daisy. Here we go. Pretty close to 800. So this thing is very accurate. Let's just go down, down, down. And where are we? We're getting closer. That was about 600. Dial it, dial it, darling. And that was 500. See, some funny stuff is happening. And are we there? Yes, we are. So that will be 500. Look how nice and clean it is in a big, big range. Way over. See, that was 1 gigahertz. So of course this one is good all the way to 2 gigahertz. Very, very nice. Let's just put this here at 2 gigahertz so we can see where the marker is. So let's do this again. Now I'm going to dial up. So look at this funny one. And now I'll go down again. And here is another phenomenon. This is the waveguide mode of the length in there. So it's almost not changing because now the plunger is getting more and more out. And then it goes back again. Oh, this is very, very funny. What is happening? Definitely it has something to do with the dimensions, and then it moves away. Oh man, this is really, really a great way to show you exactly what's happening here. They're crossing, and then we're gonna go back again. Yips, this is exactly how cavity combiners work. I don't know if we can open this thing, but I'm going to try. I don't know what kind of a super clown I am, but I just don't know how to open this thing. We got 8 screws in the bottom. Some are in here and some are out there. I just took out the first 4 and then I hear some blobbity plop and some stuff is now loose inside. And I can see some long spacers with some threads and stuff in here. And they're kind of loose now, so they don't really do a lot. So maybe I need to open the others to get in there. And the funny thing is, have you ever seen a screw made this bad? Why didn't they just throw this out and put in a new one? How bad is that? Really? The others are perfectly fine. Yeah, the slot is here in the middle, but that one is just bad. And here we go. We're in. Oh my. It is really, really heavy. And definitely this one is okay, just so you know. So there's a nice rubber gasket around here. And I don't really know exactly what's going on here. So this is how it is mounted in the bottom first, and that means that will be those mega long screws. They go through here, and then they, okay, it is definitely made as complicated as possible. So how are we going to look in this thingy? Maybe I can unscrew these and just pull up the plunger, but can I get it in again? Or I can go the safe way and have a look around here at the bottom. Probably that is much more safe, because there will be a lot of washers contacting all the way around when it's moving, and when I pull this up, it's probably going to fall down and create all sorts of problems. I don't know exactly if I'm happy about the way the connectors here, they're mounted on a flat thing, on a round thing. Why didn't they fix this a little bit smarter? This is not a super beautiful solution. So that will be copper and brass. Anyway, yeah, we're definitely gonna find another screwdriver. We are not done here yet. And here's a nice detail. I see this a lot on stuff that is made by hand. You'll see this little number here, and this mates with this number. Here is number 8. And this is exactly what the machine dudes did in the old days. They marked stuff like this. So they maybe made 10 this week. So this part number 8 and this part number 8, they made perfectly together. And probably part number 9 and part number 9, you maybe are not able to interchange the parts. Maybe the holes here, they're just drilled freehand through. So you can imagine they can't be super accurate on all the different parts and hit exactly the same place. So this is why they marked stuff how it's supposed to be assembled. Yes, I took off the bottom piece. That is actually one solid piece of brass, insanely heavy. So this is indeed the plunger, the resonant part in this system. So of course when I dial this in and out, I move this entire plate up and down, and you can imagine there's a plate here with a diameter, and this creates a capacitor to this back side, right? And of course this thing in here creates an inductor. So you can see the inductor goes smaller and the capacitor goes bigger, right? So I change the resonance point, and also I change the length and dimensions of everything in here. And like I said, let's see if I can get some light in here. I totally guessed this right. We got 2 little antennas in here, directly mounted on the end connectors. How the hell could I know that? And obviously, again, down here we got this connecting slider arrangement, and I see some oil here. This is, of course, they oiled or greased this piece here, and this oil just slided all the way down and ended down here with time. So it was probably stored like this, and it's not supposed to be stored like that. It is, of course, supposed to be stored like this, in the look like a camera mode. People would probably do it like this. I think it looks a little bit better. So this is indeed a variable cavity bandpass filter, and the Q of a thing like this is 5 to 10,000. By the way, super high. And also, I don't know if you guys know this, but you see different materials. Those are made of different materials, and there's probably also in this the threaded rod that goes from this end through another part in here with the mating part of the thread that connects here to this stuff that is moving, to the plunger that is moving. All the different materials and the composition between them and such, they are specially designed and selected to have a thermal expansion that compensate this so it stays at the exact frequency over temperature. There is a big and nasty science to the design of these things, and this is exactly why they're super expensive. I found a used one on the internet and this thing is more than 50 years old, I guess. This is really old. If you know how old this is, please tell me in the comments. But I found one online for $300, and it is not even tested or anything, and it says a good good condition. But I think this one is much more beautiful, and this one is even tested so that I know it works. Ooh, we got some. I need to handle this. This is not nice. So yes, I'm definitely going to clean up everything here. And here is the antenna. Normally you see these made so you can adjust the rotation here. I don't know if it's visible. I don't think this one was manually calibrated or adjusted. This is what you normally do when you want to optimize these things. Everything is mounted, and then you'll have some secret adjustment holes, and then you stick down a special tool, and then you bend while you're measuring, so you can make this much better. So you want to hit the super duper sweet spot of everything in there, and you need to super tweak this when it's mounted. So now I can clean this up. So the top piece looks also like brass. So it's a casted brass piece. And we've got some screws in here, 2 set screws. And then this is the threaded rod. And there's definitely a way to grab this and fine tune this so you can make the dial, so you can calibrate the dial. So I believe this is as clean as it's ever gonna be. I also cleaned this a little bit, but only at the very top cosmetic layer and the contact layer here, because you don't want to rub away the silver layer. It's really thin, but I just want this to look a little bit more clean. Of course, in here it's made of brass, and it wasn't really silvered here on the back side, and the copper here was completely corroded, so we didn't have a good contact. So yeah, I cleaned everything here so it's nice and good, and the hole fits so well. See, there's no slippity slap here. So after a lot of cleaning and everything is nice and beautiful again, it still works. That will be 500, and here is the frequency of that peak. I think this is a better zoom of how beautiful it really looks. So this is a 50 megahertz span, and the center is 500. Let's see when I dial the adjustment. I got like 5.5 dB insertion loss. So that is a little bit high on the high end, but this is also a very wide frequency range plunge combiner, so I don't know, I think it is probably not that bad. You can, of course, if you super optimize this and it's narrow band, and if this got the correct dimensions for only this frequency and everything was optimized for this, yeah, you can make this a lot less, really a lot less. But that is a whole different story.